So the N well, if you look at it from the cross-sectional view, here's the N well. It's an N-type material. So just remind me, what's the dopant for the N-type material? What's the most common dopant?
No, it's, what's the B one?
Boron?
Boron.
I think boron is
P-type.
P-type, yes.
Three.
So P-type. So just remember that N-type is N is negative, P is positive, right? So the N-type has more free what? Electrons. So who is going to contribute more electrons? Phosphorus, yes. You know, you will see a lot of different things like N well, N plus. So they are the same dopant, but the thing is, this is being heavily doped. This is not that heavy compared to this one. So these are being used as the drains and sources for the NMOSes, PMOSes. So NMOS, it's N plus is going to be NMOS. Okay, and you ask a really good question, like why you need N and P, right? So, so today I'm going to introduce that later. So just form a diode. You have a P here, and here you put them together. It's a pin junction. That's a piece of N material, a piece of a P material and N material, and put them together. That's a diode. Okay, so this is the same as this. Just keep in mind, right? Now let's get back to the shear resistance. So this is a cross-sectional view, but in the layout you did yesterday, you did the layout like that. That's a piece of N well, and these are the two terminals. The two terminals connect to where? From N well. So this is the substrate, right? It's called P sub. P sub means it's a P-type, but being doped really lightly, not really heavily. So P-type is boron, right? Boron is a dopant. So P-type substrate. So the silicon wafer is being doped with the boron to make a P-type substrate. Okay, and then got an N material, N-type material over here. But if you look from the top, that's the top of the wafer. Okay, and it's building the chip up, you know, until the very top layer. I'm going to ignore all the intermediate layers. But on the very top layer, here's the very top metal layer. It's called metal 3. And you can open it up in your design. Okay, so it's not covered by silicon dioxide. All the other materials are silicon dioxide, which is the insulator, to separate all the different layers. So if this layer is a metal 3, you have a piece of wire from metal 3 in electric vessel, you can lay it out. Okay, and you can open it up. So this is also called passivation layer. Just silicon dioxide. And you can see through. It's transparent like glass. Right? And you can see that metal 3 on the top. And when you do the wire bonding, you just bond the wire, the very thin wire to here, and connect it to the pads on the chip to make the connections. That's how you connect all the signals from the transistors. Because you can build vias, it's called vias, are also metal, kind of metal material, to like metal 2, for example, and then metal 2 to metal 1, and eventually here. So that's M1, that's M2. That's how you get the signal out. So you can imagine that this is just a resistor. And then you got a wire here, and make the connection, you got a resistor in there. So if you do the layout, you lay out as what you did yesterday, right? You lay out a N well, and you do nothing about it, just a chip with one N well in there, like 1 k ohm. And then you have all the vias going up until metal 3, and you wire bond it in the lab. And you put the multimeter here, which are getting 1 k ohms. Okay, so you build a resistor in the chip. It's nonsense chip, but just a resistor in there. I can tell people, don't use a surface mount. I got an even smaller resistor for you. Cost you $6,000 just to make a little resistor in there. What I'm telling you is this is going to be the same resistor as you have in the drawers in the lab.
How do you go about cutting out and then inserting it?
P sub, you mean P sub?
Yeah, like how do they?
Oh, how do they cut it? They dope it. It's not cutting, it's they dope it. High pressure, high temperature, and have a chamber, vacuum chamber. I don't know the details. The details you can ask the projection who's the expert on that. But you have a vacuum chamber and fill it up with the N-type material in there, and with a certain condition like temperature and pressure, it's going to get into the sub piece up.
No, like when you cut out for like your resistor, you cut out a little channel to put the.
Oh, it's not channel. It's lithography, like what you did for the microfluidics.
Okay.
You have to do this. You know, here's a wafer, right? You spin coat it. This is called photoresist, like SUA, but they are not using SUA. They use something else, but similar. Okay, photoresist. It's a type of material sensitive to light, and there are two types of photoresists. One is negative, one is positive. Depends on what's going to happen to the material after a UV exposure. For example, we are doing negative, okay? Negative photoresist. So it's a kind of really viscous fluid, like honey, and you can dump it. I'm pretty sure TSMC don't dump it by hand. Inject, right, to the wafer, like 15-inch wafer. That 15-inch, you know why this? I can do 15-inch right now? Because I know this is 12-inch. That's a stop. We don't use inches, we use meters in China. 15-inch. So you spin coat it on the wafer, make an even homogeneous layer, and then you have your mask. So what you are laying out right now, you know what? You're laying out the mask. You probably don't know that. So layouts are masks. You have different layers of those the circuit. You are thinking you are laying out the circuit. No, you are laying out the mask. There's nothing about circuit. They will be printed on the wafer as a circuit in the future, but they are not circuits. It's just a mask. All different layers of masks, and based on different process, they put the very bottom mask over here and make one layer, and then starting the second layer, metal 2, metal 3. It's called bottom up process. Now let's just do a very simple photoisography. You will understand since you have been doing that manually in the lab. Very similar, okay? So first, here's a wafer or piece up. And I spin coat a photoresistant material on the top. And here's my mask. I just place the mask. So the mask, you can design the mask where? You can design the mask for the IC chip where? Yeah, that's what you're doing right now, right? Or cadence. It's called GDS2 file. That's the final file you are going to submit to TSMC for fabrication. And eventually these GDS2 files will be printed on either glass or plastic films as different layers of masks. And that's it. So they will apply the first layer of mask here. Definitely they will make a contact to each other, so the light is not going to anywhere else. But I'm just putting it here, as you know, they physically place a mask over here. So these are ink. So the ink usually are chrome. That kind of material is not, it's opaque, so the light cannot go through. And you have a UV source here, UV source, shine UV. What's going to happen? So the ink here will block the UV, but here the UV will reach the photoresist, which is a material sensitive to UV. So as a negative photoresist, whatever being exposed will stay on the wafer afterwards. After you put a whole wafer into a chemical called developer. So only here is exposed, and the property of the material will be changed because it is sensitive to the UV light. It's a cross-link. Not chemist, but cross-link, you can imagine is sensitive, so the molecules are at the beginning not bonding to each other, but after the UV exposure, they just do this, right? But only this area. Okay, and then you place the exposed wafer in where? In where? A chemical. Okay, so that chemical is a fluid called developer. It's an organic solvent. Can dissolve for the unexposed or uncross-linked photoresist. So what's going to happen is after you put everything here, after the exposure, you just place the entire wafer into that solvent. Here is the beaker, for example, the solvent, and just put it in here with the, only this area is cross-linked, right? What's going to happen? Yeah, all the excess will go away. So eventually you got a wafer that only has this over here. That's the photoresist. That's still the photoresist. Do you need a photoresist for a chip, for the final product? Yeah, it's something blocking the dopants, blocking the, sometimes can be a metal, not the dopant, but metal, right? And then what's next? What you can do, depending on the purpose of it, right? For example, the final goal of this process is to fabricate two metal wires here and here, but not here. That's the goal of it. That's the circuit. That's metal one. How to put metal on that on the wafer? It's called deposition. It's nanometer level. Keep in mind. So you put this wafer into a chamber, vacuum chamber, and you fill the chamber up with molecules, which is called the metal material, the molecule like copper or something, aluminum. There are a couple ways to do it. It can be a chemical vapor, or it can be a physical E-beam. I might be wrong for this one, but anyway, so they can generate these metal molecules as a chemical vapor in that chamber, and that metal will deposit. You got a substrate over there, so they will evenly deposit. Did I pronounce it correctly? Deposit? Yeah, deposit. M1, right? Here. And what's next? Yeah, I don't know. You want to make it that thick. It's probably only reaching here, right? You can control the time of the deposition, so don't make it super thick. And then what's next? And there's another chemical called stripper, right? Can remove that. It's even a stronger organic solvent, right? It's not a developer, but not this one, but something more stronger, can remove the cross-linked photoresist, right? And then eventually, this one will be removed, the metal will stay. And then that's a goal. Just reach the goal. So got two wires. Very similar process. You sometimes you need a contact liner. I mean, you guys are lucky. You probably will have a chance to use it since we just got one. So Jesse just got one last year. A contact liner. This all these. So from UNLV, which is the R1 institution, they had two contact liners, but none of them are functioning. And UC Irvine, they only had one. It's a 30 years old one in the nano lab. You have to get trained, thoroughly. UC Irvine is like top 30 university. I only have one functioning one, but 40 years old. I think we are lucky as a super tiny institution. We have a contact liner, and Dr. Jesse probably in this class will have a lab on how to use it. Maybe, I don't know yet, but there will be definitely a lot of photoisography. That's the name of it. Experiments in that class. It has a lab, right? So you will eventually make a parabolic transistor or a very simple diode in that lab. I'm not speaking for him, but it's going to be something similar, right? So you'll learn. Yeah, they're just different dopants. Mm-hmm. Very exciting, right? I haven't even done that. Only Photoisography was microfluidics. I've done hundreds of these. Okay, that's page number 2. Anyway, so this answers your question, I think. And next, we were talking about the resistor for the unwell resistor. And it's a 3D structure, even though it looks 2D on the paper, but it's a 3D structure. Like that, okay? So that's the unwell resistor. And that's the width of it, and that's the length, and that's the thickness. Okay, and the resistance of the resistor, not just for unwell, but for all the other materials, is the resistivity times L over A, right? So A is the area here, but in this example, it is rho times L over W times T. That's the resistance of this unwell. And because you couldn't change T really, because that's depends on the per size, they deposit that unwell following a certain per size during the in the foundry. So it's going to be a certain thickness. It's not changing, so T is not changing. So rho and T are the constants, but only L and W are changing. Right? So you cannot change this anyway. If you for L, so the resistance of the unwell material depends on the ratio of L over W. Okay, so if you have a L to be 100 and W to be 10, this becomes 10, right? And you have L equals 10, but W equals 1, and the ratio is still 10. That's why it doesn't make sense to make a bigger L and bigger W to make the same resistance. So that's why you want to use the minimum of what, and then change what, make a resistor. Yeah, yeah. Mm-hmm. So if you have that, so the minimum width is defined by the per size. If we are using C5, there will be a minimum width. I think it's on the lab instruction. So so this is the top view of the resistor, for example, the top view of the resistor, and it is this long, right? And this equals this. This is L, this is W, and the ratio is 1. So this is 1 square here, and just calculate how many squares you have in the resistor to find out the resistance. And this is called the sheet resistance. Why? Because if you have a square like that, or if you have a square like this, do they have a different resistance? No, it's just 1 over 1. It's still the same ratio. So this is called sheet resistance. And for C5, it's 800 ohms per square. So if you have a certain length here, and over W, you get the ratio, and times 800, you get how many squares, which means how many 800 ohms you have in the resistor. So you can design any arbitrary resistance for the resistor under unwell. Make sense? So that's unwell resistor, how to calculate the resistance of it. And here, pin junctions, really quickly. So learn the very similar things in analog as well, I believe. So if you have a P material and N material and put them together. So as I said, for the P material, I have a lot of free holes in here, right? For the N material, I have free electrons. If you put them together, what's going to happen? Yeah, it's going to diffuse because they have a concentration gradient over there, right? The electrons are going to fill the holes in here, so the holes are being filled up, and then eventually become negative charged. You are thinking, why is not neutral? The holes are being filled up with the electrons, should be neutral. And now there's another concept. So for a silicon wafer, just a piece of silicon, is that neutral or positively charged or negatively charged? Yes, neutral, right? What about the p-type? It's not. Still not. This is a very common mistake people are making. It is still neutral. Is that amazing? Why? You're learning analog anyway, but I just want to introduce it. So we have to deal with MOSFETs later. I have to understand this first. I'm going to follow the progress in analog, so I have to do it first. Anyway, so why is this neutral? No, is silicon. So hey, let's think about that. Is silicon neutral? Yeah. Is phosphorus neutral? No, phosphorus. God, if it's not neutral, just grab phosphorus and generate electricity for the car. It's just phosphorus, right? It's just a material. Is that neutral?
Yes.
You put them together, it should still be neutral. It shouldn't generate charges. It's still neutral. This is how you understand them and remember it, right? Neutral point should be still neutral, all right? So it's still neutral. What about N-type?
Neutral.
Yeah. If it generates charges, then you are generating energy for, as a battery. It shouldn't. Okay? Now here is a different story. I put a P is neutral, N is neutral. I put them together. What's happening? So it used to be neutral, right? It used to be neutral, right? But when these guys diffuse to here, you just got excessive, just more electrons. Then what's going to happen here? It's going to fill up the holes. It's called depletion region here. Depletion region. Why? It's because it depletes the holes here. So no holes anymore because all the electrons move over, and there will be more. It won't be just about the right number of electrons. There will be more when it diffuses over, right? So this part becomes negative charged. Now, you know what I mean? Because you got more electrons. It used to be neutral. I got more electrons. It's going to be what? Yeah, this is negative charge. Make sense? What about this part? And what's the name of the region here? Depletion region. It's a p-n junction. And what is a p-n junction here? It's a diode. The diode you use in the lab is a diode. Okay, and if I connect a battery to it, ignore the whatever the current is going to burn it. So just assume it won't burn an ideal diode with a battery. What's going to happen? So if you have holes here, it's positive charge and negative charge. What's going to happen here? What is this called? Electric field. Okay. So it has a certain width here. All right. But when you are trying to add a battery. So here's P, here's A, here's C, right? It's anode cathode, the battery. So anode or plus is connected to P, and negative is connected to N. This is called forward bias, where this diode is being forward biased, right? It's a forward bias. What's going to happen is like you have a diode, and connect a battery to it. What's going to happen? It's going to pass a current to it, right? As the current's going to flow. What's happening here when the current flows? It has a depletion region, right? But when you forward bias the pin junction or the diode, it's going to make this depletion region thinner. Yeah, why is that? You have electrons here, right? And you positively charged this part, so electrons is going to be attracted to here. So you got less electrons. So the depletion region will become thinner. Same to the holes. Whenever it's thin enough, what's happening? What's going to happen? Yeah, so the electrons is going to, so you are getting more electrons here to tunnel through. Like a stream of electrons flowing that way. And what's happening? What's happening? The diode becomes conductive. It passes the current like a short circuit, freely flowing the current in the circuit. That's how it happens. That's what's happening here. If you connect the diode and forward bias in the circuit, this is what's happening there. So one quick question. If you forward bias a pin junction, is the depletion region get thinner or thicker? Thinner. And there's another concept that's called junction capacitance. Depletion capacitance. Why there's a depletion capacitance over here? CJ, I mean, it should be a junction capacitance. Just give a different name. Depletion capacitance. No, depletion. Yeah, but this will call it CD, not CJ, right? The CJ is a junction capacitance. Anyway, CJ is depletion capacitance. It's a capacitance between these two. It's a difficult to understand anyway. So it has an electric field, and these two terminals are considered as conductive. I got two plates and got an electric field. It's a capacitance. It's a capacitor. So this becomes a capacitor. So capacitance is defined as what? Epsilon times A over what? D, right? So what is A? Plate area. Does that make sense? You got a larger A, you got a larger what? Yeah. It's just more this larger area to hold more charges, right? And you have a larger D, that's a distance, right? Distance between the two plates. Larger D for larger or smaller C. Smaller. So you have the same two plates, but you move it further away from each other, then the capacitance will be smaller. Okay. So for this case, if you forward bias the pin junction, CJ will be thinner. No, CJ was
larger.
No,
Forward bias
it becomes thinner.
Oh,
really?
Make sense?
Yeah.
Okay. Now let's look at what about the other way? What's the name of it? That's a good name. We should change it. Just attend one of the IEEE meetings and tell them it should be backward bias. It makes sense, right?
There's still a depletion region.
Yeah, you'll never get rid of it. What are these charges here? Don't cheat. Don't look at our notes. I'm making eye contact with you. Yeah. So this is called reverse bias. English is difficult.
Yeah, you call it reverse bias,
right? And what's going to happen? Yeah, why? How do you understand it? I mean, since I just told you here, this will attract more electrons, so to deplete more electrons or remove electrons from here, right? What about this one? Or you can think about this is a cathode, right? It's negative. It's going to add more electrons to it, make it thicker. Yeah, so you're getting a thicker depletion region. And CJ will what? Will do what? Okay. Let's see what else you guys know.
The one that makes the electricity coming by one light, right?
Yeah, I was trying to show you that it's bigger, it's thicker. Yeah, what you mean?
So current can't pass once it gets too thick.
No, it can still pass, but it's just leaking. Yeah, you are right. Actually, ideally it shouldn't, right? So when you are learning doing that in circuit 1, you were told that this should block the circuit. Shouldn't have any current flow through that. That's why the symbol just drew a little line here, meaning blocking any current. Yes, in circuit 1 level, you consider this as a disconnect circuit. But when you get into analog, it's actually leaking something in there. And remember the photodiode? The photodiode thing?
Okay.
Right? So it's a different diode. They have different concentrations of dopants, right, for photodiode. So the diodes can be used for so many things, so many ways. So the regular diodes are being used for the power electronics to make all these rectifiers right after the transformer. Okay, you got AC, you block it one way, so eventually you got all the bumps, right?
Yeah.
And then you pass this through a what? To get a DC. Low pass filter. Why? Because these bumps are considered as high frequency, so they will be attenuated and only DC because it won't be able to. The circuit is a low pass, so the circuit is not fast enough. It won't be able to charge and discharge the circuit efficiently. That's why it's going to stop doing that. Still got a little ripple here. So these are called ripples. And that's one of the specs you want to evaluate. Do you have a lot of ripples for the power regulator? If you have a lot, then it's not a high quality. So the ripples should be very small voltage range, like millivolts range. But anyway, so the diodes, after diodes using the low pass filter to regulate it, to not regulate, how to say it, rectify it to DC voltage as a power supply, for the power supply. That's how you convert AC to DC, right? Mm-hmm. And you need the diodes for power electronics to supply, to rectify, for rectifiers. And you need the diodes for voltage multipliers, which is the circuit I just patented. It's part of the circuit. It's being used to amplify DC voltages. For voltage multipliers, you will learn that as well in analog for the circuit in detail. And you can use the diode as, what is LED? What does LED mean? Yeah, light emitting diode. It's a diode, right? So it's just being made in a different process, and you don't want to package it into a black rod, so it won't see anything, right? So that usually they are just have a silicon dioxide or see-through material on the top. So you power it up, you can see light emitted from the diode. That's also a diode being doped with different concentrations of materials.
So if you got two really big plates of like P-type material and N-type material,
Yeah.
and you shove them together, you can make a really big LED.
Have you done that?
No.
What did you mean? I mean, say it again.
No, I'm just wondering if it was possible. Like,
Say it again. What kind of?
so if you took like a full wafer of P-type material and a full wafer of N-type material,
Yeah.
and you sandwich them together,
Yeah.
you can make a really big, like 15 LED.
Diode.
Yeah.
I don't know if it's able to handle that kind of heat generated from it, right? But you don't have to use you don't have to use two wafers. Why two wafers? You can just use one wafer.
Whose bigger is better?
Maybe. It definitely has more.
15-inch LED.
Yeah, it definitely has more area to emit lights. But it's gonna be super expensive. You know, keep in mind, the LEDs should be super cheap, right? So remember the 15 inch, right? 15-inch wafer, and we used the Muse. It's a multi-project wafer, MPW. You should know that for the interview. If you tell them we submit our project to MPW, good. So multi-project wafer. So it's a wafer not just dedicated for your project. So that's why you can lower the cost. So the 15-inch wafer like that, we only used a little tiny area over there, and that's $6,000. If you use the whole wafer as one diode, so it's going to be a $1 million diode, and you only use it for what? Yeah, for celebrations for the king,
I want to light up
UK or something. I don't know. Anyway, so won't be really practical. But you know, after I introduced all the applications for diodes, there are so many different kind of diodes. They're just PN junctions, right? But being fabricated in a different way using different materials. So what about this one? Remember? One quick question here. Which one is non-inverting? Which one is inverting?
That one.
Which one? Which one is the inverting terminal? Which one is non-inverting terminal for this? What's the name of it? Anyway, that's a pixel, right? Remember? Always negative feedback. You forgot that? Negative feedback. No. But the feedback has to be negative. Keep in mind. Sometimes you flip it, but you know you are talking about the non-inverting, right? So it's here. You got a signal input for the non-inverting, but still.
Well, no, sometimes they also have positive feedback.
Really?
Yeah, but that's
Not.
only for systems.
Oh.
It gets weird.
Yeah. On the textbook, right? Anyway, it's. I think I have seen some examples using negative positive feedback, but very rare. So you don't have to really care about that really much, unless you are. Yeah, unless you are.
I mean, it's because you threw that out there because you wanted to show us that that's your things.
Yeah. Anyway, so for general purposes, for signal amplification, negative feedback. Also here, right? Negative feedback. And what's the name of this amplifier? Yeah, transimpedance. What's the? Yeah, TIA. Transimpedance amplifiers, right? So what's happening here? What is this called? Okay, non-LED, all right? Okay, it's the opposite way. LED is you put a voltage, emit light. This is receive light, convert into photocurrent.
Don't LEDs work as photodiodes, or is that wrong?
They have different process. I don't know what, but different concentration, different materials for it. But if you put the LED here, it's gonna do similar things, but won't serve the purpose of it. So photodiode receives light, convert it into what? What's the name of it? Photocurrent. So the photocurrent is gonna flow that way, right?
Yeah.
And flow through the resistor to generate what? What? Yes. Good tip.
We finish each other's sentences.
Sandwiches.
Sandwiches, yeah.
All right. Then you got a voltage. Okay, so convert the light into voltage. Why we always want to convert into voltage? So for example, the PMTs, some of the PMTs will directly output, or it's a photosensor. I haven't used it before, but it is a photosensor. Some of the PMTs outputs current signals, and you have to connect the TI to it, convert it to voltage. And some of the PMTs directly outputs voltages because they nicely already put a TI in there. So directly, get a voltage. Why we always want to convert all the signal to voltage? That won't pass the interview. Think about it. Because all the ADCs are analog voltage ADCs. Why you want to consider ADCs?
Because when we split the wires, will stay the same instead of current. That, well, that's what you're finding on this.
Yeah. So what's the most powerful machine for everyone right now? Computers, right? The computer is the digital computer. It's not an analog computer, the digital computer. So you want to digitize it whenever you can, as early as you can. Why is that? Why you want to? So less noises, yes. So for example, analog signal, right? If there's a little noise, it's going to bump it up, and you get a different signal here. Or about digital signal? A little noise, it's okay. I know it's still logic high. It's not a unicorn, right? It's still one. It's not a horse, right? It's more resistant to what? Noise. That's why whenever you can, just convert into voltage as soon as you can before getting too much noise in there. And then you can digitize it. It's ADCs, and so you got digital signals and computer interface with the computer, with microcontroller, computer, whatever. And after that, for the communication in between computers, in between digital chips, do you still need to DAC it, or just use a standard digital communication protocol? Yeah, just digital. And you want to use the last number of pins. So what are these protocols? You have learned it. Or the I2C, SPI, UART, USB, right? All these kind of things you will learn in microcontrollers. Not too many, just all of these. Just learn it. So this will, how many wires in here? It's a quiz question for Max. For communication, not power and ground, but just data. No, 2. 8 is not good. 2. So just 2 wires for all the communication. One is clock, one is data. Just one line for data. It's amazing. So we need to follow a protocol. Why do we need a protocol for digital communication? It's all the signals are 0 1s. When do you know it's going to start the signal, but not something else, right? So for example, I'm communicating with you right now, and it's only 0 and 1, 0 and 1s. When do you know I'm going to start sending the message, but not something else? So you need to follow a certain protocol. Okay, you have, so for I2C, I remember it's you have to pull it down to 0 first. You pull it down to 0 first, so the other device will know, okay, this guy is going to start telling me something. Okay, I pull it down. Same wire, same wire. The same wire only have same voltage, right? So for the master or follower, you don't want to use the other word. Sometimes it's going to censor, but master, you pull it down, so the follower will understand it, because it is able to sense the voltage because it's the same wire, right? And then followed by the address. The digital device has the memory, all the different addresses, and follow the address. I want to take data from some address here. It's 8-bit address, FA or something. It's a hex number in there, and then start sending it, following the clock. Every rising edge is going to trigger one data in here, like 1 1 1 1 0 0 0 0. So I know it's F0. Okay, so and the protocol understands that the first hex number is the address, and followed by the data, right? If I'm writing to the follower, The first hex number is address, and the following hex number is data. So I'm going to write that data into that address in the follower. That's how we finish, how the different devices finish a very simple 1-byte communication. Just one wire as a protocol. I have to, because when we are talking randomly, you won't understand when we are going to start sending the critical or the essential message. I have to tell you, hey, I'm starting talking to you, right? And then you know I'm going to send you a message right after that. So you want to use as fewer numbers as possible because you don't have that many pin resources on the chip. So I2C only 2 pins, which is amazing. SPI is 4, UART is 2, USB is 1. Is that 1? Maybe more than that. Okay, but you can send 32-bit data just using this. If you don't do serial, so all these are serial, which means it's just one line and follow protocol. If you don't do that for 32-bit data, if you do it parallel, how many pins do you need? 32. Yeah, one more for the clock, right? I got 32 pins just for sending that data, but nothing else. It's going to occupy all the pin resource. So your die is only this much, this big, right? I only have 33 pins. Can only do that kind of communication, but nothing else. So that's why you want to do serial, not parallel. But when do we want to do parallel? And in the old days, you look at the ports from the old computers. These are parallel ports. You remember no, they don't have serial protocol. They didn't have it. So the old computers, you will see from the back of the tower, you'll see the ports. You couldn't even count how many are in there. Like huge port. These are parallel ports. And but now if you look at the very new ones, you don't see that anymore. Okay, but still useful. When do you do it? When do we use parallel? Yeah, but where? What is that? Like an old computer?
The spaceship that landed on the moon.
Oh. No. you still need a digital chips and serial communication. It just speed up the clock. And sometimes you have a pretty large technology like C5, because these transistors, so for example, the C5 is 500 nanometer, like this. I know this is bigger than that, but I mean, just like, for example, this is a 500 nanometer transistor. So the 2 nanometer transistor right now is going to be how much? Like only this much, like compared to the 500, right? So you can imagine there will be a lot of capacitance for the bigger per size, which means you cannot toggle it really fast. That's why we want to use smaller pro size because it's faster. That's why your phones can be more powerful, a lot faster every couple of years. Or using 2 nanometer, 5 nanometer technologies, way faster than 500, right? Do we still have time to introduce more things? Only have 3 minutes left. Probably not. Should we call it today? Do you have any? Friday. It's DNL and ILs for DACs. I think the next will be the time delay for the unwells. But the example is pretty long. I don't think we have time today to do that. Let me see what else I want to talk about here. So the place we can use parallel communication is still not directly for the IOs for the chips, but inside the chip. You can have 1,000 wires inside the chip, right? If you for the internal communication, if you use parallel, it's gonna be a lot faster than serial. They don't use serial internally inside the chip, like IPGAs. You have the internal wires. Remember, you can define a wire with 8 to 1 or 31 to 0 or something. So these are all parallel buses, which will be fine because it's faster and directly. So usually, if you have a rag data type, they will be able to send all the data at once just through through one clock. So all these in-chip communications are still parallel. But for all these external pins are serial for the modern communication with the modern chips, digital chips, right? I think that's it for today.
I would rather ride my road